Practice problems. A wooden rod of mass m in length L is pivoted on a frictionless axle that passes through its top end. So we have an axle right here. This is the axis of rotation. A small piece of clay of mass little m, which is equal to 1/2 m, is fired with an initial velocity v0 into the exact center of the rod. The piece of clay strikes the rod and sticks to it. And here the moment of inertia of the rod about its end is 1/3 mr squared. A. Is the linear momentum of the clay rod system conserved after the collision? B. Is the angular momentum of the clay rod system conserved after the collision? C. What is the angular velocity of the clay rod system after the collision? Alright, first, is the linear momentum conserved? No. This axle is exerting an external force on the clay rod system. If there was no axle, this rod wouldn't even rotate. It would just slide translationally to the right because the clay is hitting right in the middle. And it's not going to do that. Instead, it's going to rotate because of an external force. Therefore, the net force does not equal 0, and linear momentum, therefore, is not conserved. However, angular momentum is conserved. So yes, there is an external force. However, this force is not exerting a torque because the force acts at the axis of rotation. Remember, torque is RF sine theta, where R is the distance from the axis of rotation to the point where the force acts. In this case, that distance is 0 because the force is acting at the axis of rotation. So, that force does not apply a torque. Therefore, there are no external torques acting on the system. Angular momentum is conserved. Now let's go ahead and calculate the angular velocity of the clay rod system after the collision. The initial angular momentum, L0, is calculated about the pivot point. So initially, the rod's not moving at all. It doesn't have any angular momentum. However, the clay is moving. Therefore, it has angular momentum. And remember, when something is moving in a straight line relative to some other axis of rotation, you use this equation, Rmv sine theta. So the distance between the axis and the point of collision is L/2. The mass of the clay is 1/2 m. The initial velocity of the clay is v0. Simplify that, we get 1/4 Lm v0. So this is the initial angular momentum of the system. On the previous slide, we calculated the initial angular momentum. Well, it's going to be equal to the final angular momentum since it's conserved. When the rod with the clay stuck to it is rotating, that's just an object with angular momentum, where the angular momentum is I omega since it is rotating. But the catch is that once the clay sticks to the rod, the moment of inertia of this object changes. So we have the initial moment of inertia of the rod, but then we have to add in the fact that we have added some mass. Now, when you add a piece of mass in, you're going to have to add mr squared for that mass. The mass is the mass of the clay, which is m/2 here. The distance at which it hits, so if that's the axis, the distance, the whole length of the rod is L, therefore this is L/2. And remember, it's mr squared, so that gets squared, times omega. We can go ahead and set all of that, which is simplified here, set it equal to the initial angular momentum, solve for omega, and we get 6/11 v0 over L. A thin, uniform rod of mass m and length L is initially at rest on a frictionless horizontal tabletop. A small sphere, m, moves perpendicularly toward the rod with an initial velocity v0 and strikes the rod at the bottom end. After the collision, the sphere moves in the opposite direction with a velocity of 1/3 v0 to the left, so it's negative. The moment of inertia of the rod with respect to its center of mass is 1/12 ml squared. Remember, in this problem, there's no axle holding the rod in place. It is free to move translationally across the table while also rotating. The questions are on the following slides. A. Is the linear momentum of the sphere-rod system conserved after the collision? Explain. Yes, it is. The net external force on the system is 0. Therefore, linear momentum is conserved. Unlike in the previous problem, there is no axle exerting an external force on the rod. The rod is free to move across the table. Therefore, linear momentum is conserved. B. What is the velocity of the center of mass of the rod after the collision? So we're looking for this VR here. We're going to use conservation of linear momentum. Initial momentum equals final momentum. You can ignore the fact that this is rotating for now. We're just focusing on the linear motion of the two objects. Initially, only the sphere is moving with an initial momentum of mv naught, right? Because the sphere has a mass of little m. So little m v naught. At the end, we have two objects that are moving in opposite directions, which means, so if to the right is positive, that means to the left is negative. So now the sphere has negative momentum, and it has a momentum of mv naught over 3, since that velocity is cut in third. And the rod now has linear momentum, mv. The mass is capital M, and that v sub r, that's what we're solving for. If you simplify this equation, we get that the final velocity, linear velocity of the rod is 4/3 little m v naught over big M. C. Is the angular momentum of the system conserved? Explain. Yes, it is. There are no external torques on the system either. Therefore, angular momentum is also conserved. D. What is the angular velocity of the rod after the collision? So here we're going to use conservation of angular momentum. Initially, the only momentum in the system is due to the sphere, which is traveling in a straight line with respect to this object. Now, this object does not have an axle, but it is an extended object. Its axis of rotation is going to be at the center of mass. Unless you have some sort of other axle that changes that, this is going to be the default, right in the middle, is where it will spin. So what we can do is, in reference to that axis of rotation, we have the angular momentum of the sphere is mvr sine theta, but this is a 90-degree angle, so the sine theta becomes 1. The mass of the clay is little m, the velocity of the clay is v naught, and the distance from the axis of rotation, which is from the center of mass of this rod, is L over 2. After the collision, the ball of clay now has negative angular momentum with respect to this axis of rotation here. So we have negative m, still has a mass of m, the new velocity is v naught over 3, and it's still with respect to this axis of rotation, and that distance is still L over 2. But now the rod is also rotating, so it has angular momentum. Now it has regular angular momentum, which is I omega. When I say regular, I mean not this version for an object moving in a straight line. It has the version of an object that is rotating. So what is the moment of inertia about the center? 1/12 ml squared omega. So there we have our angular momentum of the rod. Solve this equation for omega, and you get 8 mv naught divided by big M L. Disk A, with a mass of 3m and a radius 2r, is rotating with negligible friction at a constant angular velocity omega naught. Disk B, with a mass of m and radius r, initially not rotating, is lowered coaxially onto disk A. What is the angular velocity of the system of two disks?
So here's our givens right at the top. We have disk A with a mass of 3m and radius 2r. So that's down here. That's disk A. Disk B is up here, and that's lower down on disk A. And we have to find the angular velocity of the system of two disks. So we're going to use conservation of angular momentum of the system, where the initial angular momentum is equal to final angular momentum. There are no external forces here. So here we have I0 omega 0 is IF omega F. So initially, this is block A here, disk A, that has 1/2 mr squared. Why is that? Well, we wrote that up here. That's the moment of inertia of the disk. The mass is 3m, radius is 2r, and here's omega 0. After block B drops on block A, we still have the moment of inertia of block A, but now we have to add the moment of inertia of block B, which is 1/2 mr squared, and both of them combine to form one system, so we have omega F. So you go through the math here, we're leaving that to the reader, and omega F, the final angular velocity, is 12 omega 0 over 13.